Hey guys, I wanted to do a video that really did explain better how the chain rule works. Okay, but we need to do a little bit of review on how derivatives in general work. Okay, so what I've got here is a function in green, which is f. Okay, and then I choose some value x on the x-axis, and then you go up to the green curve and then to the y-axis to get the function value of x. Right, so that can be moved around. I've also got at this point the tangent line there. Right, so this thing right here is the tangent line. Okay, I have this other line right here, which is the secant line through a second point, so you start at x and you go forward by delta x, and then that's a new point on the x-axis, and then you go up to the curve and over to get its function value. So at x plus x delta x, we go up and then over, and we find f of x plus delta x over here. So this is the x. So the coordinates of this point are x, f of x, and the coordinates of this point are x plus delta x and f of x plus delta x. Okay. And the secant line will become the tangent line if we make delta x go to 0. Okay. And now we talked a little bit about what linear approximations are, and if you zoom in, this tangent, see how this tangent line becomes kind of indistinguishable from the green curve? So depending on how far out you get, this is what the error in that linear approximation would be, because this is the true value of this nearby point, right? If it's nearby, the true value lies barely above the approximate value using the line. Okay, so I want you to see how rapidly that orange error just disappears, even though we have a relatively big delta x, relatively big delta f. Delta f is just the change in f, and delta x is just the change in x that we've done. Okay, now the question I really want to ask is this little line right here. I've labeled it as f prime of x delta x, and why is that? Well, alright, this being the tangent line has slope f prime of x, right? This x. If I plug this x into the derivative, I get the slope of the line, the slope of the tangent line there. Okay. Maybe I'll make this secant line a different color, just so we don't get confused by it, right? That's the secant line, that's the tangent line, and they become the same line in the limit. Okay. Okay, well, so why is this vertical line segment right here equal to f prime of x delta x? The slope of this thing, the rise over run, is given by f prime of x, this x here. Okay. But so rise is this line segment, and run is this line segment, and this run is delta x. So if I take this quantity here and divide it by delta x, I should get the slope. And yes, indeed, this thing divided by delta x is just the derivative. That's why this thing has to have that magnitude. And as long as you make your delta x small enough, f prime of x times delta x looks very similar to the change in f. Alright, if you take the derivative at this point, multiply it by the change in x you've decided to do, it pretty much gives you the change in f. Now why? Why is that? Well, let's come over here and take a look. Okay, so remember what we mean by derivative. The derivative of a function is the limit as h goes to 0 of f of x plus, I'm going to use delta x, of x plus delta x minus f of x over x plus delta x minus x. Now why? What is this? This is a slope, right? This is, you could think of this as y2 and y1 and x2 and x1. Why? Well, what is x2, y2? It's x plus delta x, comma, x plus delta x. This point here is x2, y2. And x comma f of x is this point, right? So what we've done is found the slope of the secant line. Without having the limit there, this thing is the slope of the secant line. But what the limit is saying is that delta x is slowly collapsing to 0 and the secant line becomes the tangent line. Okay. And that error in any linear approximation you try to do goes down. So in other words, if we don't quite let delta x go to 0, if we let it be small, then this must be true. The value of the derivative is approximately equal to the slope of the secant line. Right, if we're not taking the limit, then we're no longer, and you can see that all I get down here is delta x once I cancel my x's. So, so this holds because delta x is presumed to be relatively small. In other words, we're like this. Okay, and if I multiply by delta x, I get this numerator is equal to f prime of x delta x. Then if I add this over, I get this important result. This is approximately equals to. So the function value of the nearby point plus this thing right here. Now normally if we take f of x and add delta f to it, we would get exactly this, right? Let's spread this out. Right? If you take f of x and add f delta f to it, you get here. So this quantity, this minus this, is delta f, right? Oopsie. This minus this. So what this is saying is that what this one was saying right here is exactly what I was saying before. This thing right here is delta f, right? It's this number minus this number. That's how you get this magnitude. But this guy right here is this little person, and that's why they're approximately equal. Okay. So, but this thing here is telling us that we can do linear approximations, because you just take this function value that you know because you've chosen like an easy x, and then you want to know something very, very close by. You would, you know, if you added point, if you just go off by a tiny little bit, just use the tangent line to do the math rather than the green curve, is what this lets you do. Okay, and this little error is pretty small as long as you choose a small enough delta x. As long as you don't move too far away, then you're in flatland, right? As long as your delta x is really small, then you can pretend the curve is flat. It's locally flat. It's only globally curvy. Okay. So we ended up going with this approximate thing, which you can see geometrically here. Adding that over and we get this result. Now this result is going to give us everything we need. This linear approximation idea. Okay. Because if this is true, then suppose f is a composite function. Okay. So suppose the f in question is in fact a composite function. Okay. Well, then what is this saying up here? Well, so then f of x plus delta x, that's the same as g of h of x plus delta x. Now, what can we do with this thing? Well, what's h of x plus delta x approximately equal to? Well, just replace the f with h's and you can see what would happen. So this will be approximately equal to g of, instead of h of x plus delta x, it'll be h of x plus h prime of x delta x. Right? That's what it would be. Now, let's consider this expression we've got in here. What does this look like, this h prime delta x? That looks a heck of a lot like what, now if we have some other function, h or whatever, choose an x, and then x plus delta x, right? And then we have the tangent line there. So this value is h prime of x delta x. But this entire value here is delta h. So this thing is an approximation of delta h, because delta h is coming over here like this. Right? But that's the tangent line. This little guy right here, this part of it is h prime delta x. So what that means is that we can say that this is approximately equal to g times h of x plus delta h. See? This thing is approximately delta h. So I'm just going to call this h. I know we're at x, but who cares? What is going on in here? So instead of doing an f of x plus delta x, we're doing a g of h plus delta h now. Aren't we? So we can then say that that is approximately equal to what? The function evaluated the first thing, so g of h, plus the derivative of the outside thing evaluated at the first thing, right? So plus g prime of h times the second thing in there, delta h, right? This is approximately this. Okay. So, what is delta h though? Really? We can undo that. We can now replace this thing with that again if we needed to. So I'm going to do that. I'm going to say that this is g of h of x, okay, plus g prime of h of x times, what is delta x again? Is this thing, right, approximately? So h prime of x delta x. Just instead of using delta x, I'm using this thing because they're basically the same, right? This magnitude and this magnitude almost agree, and they absolutely agree in the limit. Okay, well, what have we got here? We have f of x plus delta x is basically this, okay? But this right here is another way of representing f of x plus delta x. So if I combine those, I get f of x plus f prime of x delta x. That's this thing equals approximately this thing. This is like a summary statement of all this stuff. Okay, good. Now, this is what we've been after the whole time. I want to know what is the derivative of a composite function. So I want to isolate this f prime. What's f of x? That's g of h of x, right? That's how we defined f. Right, this is the thing I'm after. This delta x. Okay, so these cancel. So I have f prime of x delta x equals g prime of h of x, h prime of x delta x. These multiplicatively cancel because it's not 0. So I get f prime of x equals g prime of h of x, h prime of x. This is the chain rule. Okay. That's the result, and it really comes from this concept of linear approximation. We're just doing it twice. Okay. So I hope that clears up any confusion that you might have about what the heck is going on with the chain rule. It takes a lot of practice to use this thing, but what this statement really says is that f prime of x is really the derivative. Let me fix that. It's that the derivative with respect to x of g of h of x is this, right? Because this is how I had defined f. So f prime is the derivative of it. Okay, so that's a huge result, and this is basically why it's true. This isn't exactly a rigorous proof, but it could be made more rigorous, I think, though, at the expense of clarity or intuition. So, you know, who needs to be rigorous anyway? This is good enough for me, so hopefully good enough for you. Thanks for watching.